We're going to start a crash course in metric geometry, and so the content of this course is this. So we will having 4 lectures on these topics and 2 extra sessions on these topics: Hausdorff measure and length, Riemann manifold as metric space, a length metric on covering spaces. Okay. So we'll start with lecture 1. I will start with the definition of metric space. And so basically a metric space is a set X together with a metric distance function which satisfies some properties. What are those properties? The first one is d of xy is 0 if and only if x is equals to y. Second property is a symmetric property. And third property is the triangle property. Okay. So a metric space is a set X with this distance function d which satisfies these 3 properties. Okay. So from these properties, it is easy to derive that basically d of x comma y is always non-negative. Okay. And one can basically prove something more. So this is, I will write as an exercise. This will be like, so let us define a function f such that x cross x to r, okay, and defined by f of d of x comma y. So this is basically continuous. Okay. Okay. So now let x comma d be a metric space, and a curve is a continuous function gamma from a closed and bounded interval a comma b to x. Okay. And I will denote I will say alpha is an arc if it is an injective curve. So if so let us say we have a curve gamma. If gamma of a equals to x and gamma of b equals to y, then we say that x and y are endpoints of gamma, and that gamma joins x and y. Okay. So there's one thing which I want to mention, that curve is not a set but a mapping. Okay, like by this what I mean is that a same set can be parametrized by different kind of functions. Like this is a set, suppose, and we can have gamma 1 and like from some interval a comma b to x, so that gamma 1 of a comma b is basically this line, this curve, and also gamma 2 from some interval c comma d to x to this line. Okay, but we will see that how this set is related to these parameterization. That will be a part of extra sessions. So yeah, so the curve is not a set, it is a mapping. Okay, so one example of a curve is graph of a continuous function. So we have f such that we have some continuous function a b to r, okay, and we just take the graph of that function t comma f of t, and this is a curve. So this is a curve in R2. Okay, so there are some kind of curves like which is known as space filling curves, first introduced by Peano and then by Hilbert. Hilbert gave another example of Peano curve. So it says that there exists a continuous map such that the continuous map from f0 comma 1 to R2 such that f of the range, the image of this interval under f is basically the square. So that's why it is known as the space filling curve, because it is filling all the square. We basically don't want to work these kind of curves, and one way to kick that out is to introduce the notion of rectifiable curves. So this definition will be familiar to all of you, I guess. So let P denote the set of all partitions of A comma B, and the length of a curve in the metric space X comma D is denoted by LD gamma, and is defined as LD gamma equals to supreme over all the partitions, and we take this variation. The distance between gamma of Tk to gamma of Tk plus 1, where K is running from 0 to n minus 1. Okay. This is somewhat familiar to the bounded variation once we have a function f such that a, b to r. Okay, the way we define the bounded variation of f. Okay, we say that a curve gamma in xd is rectifiable if this length is finite, and a metric space is said to be rectifiably connected if every pair of points x comma y in x can be joined by a rectifiable curve. Okay. Okay, so these are some easy results to establish. The first one is d of x comma y is less than equals to the length of the gamma. So we have a curve. So we have a curve joining 2 points x and y in x. Okay, so distance between these 2 points, d of x comma y will always be less than or equals to the length of this curve gamma. Okay, so like to prove this, you just have to take the partitions a comma b. Okay. Okay, and the next property is the length of the curve gamma is 0 if and only if gamma is a constant curve. This we'll just see right now. And the other thing is, so in discrete metric space, the continuous functions are constant, so we only have the constant curve in the discrete metric space, and the length is going to be 0. So, yeah, yes.
So in the last example, for the space filling curve, it's not rectifiable, right?
Yeah, that is not rectifiable. Yeah, the space
Okay,
filling for curve is not rectifiable.
Is it very easy to see?
Okay, so this is the core idea of this space filling curve is like they are basically the uniform limit of a sequence of curves. Okay, uh,
Okay. Okay.
and
Okay.
and we will see that this the length is not preserved under the uniform limit. It means that you take a
That goes
sequence
to
of, yeah,
the length goes to infinity as the
yeah,
sequence converts.
yeah, yeah,
Oh, ah,
in that sense, yeah. Like here also, like if you want to construct a non-rectifiable curve in R, okay, so if you want to construct a non-rectifiable curve in R, so what we do, just wait a minute. Okay, yeah. So what,
so if I if um, if
Mhm.
if I consider all the curves,
Mhm.
which is the spaces of all curves,
Yeah,
and define a function from that space to the real number, the curve goes to the length of the curve, then
okay,
that is not
that function is
like
not continuous.
continuous. Even if I don't know the what the topology can be defined also there in that
Yeah,
set
that
of,
is a uniform, yeah,
but the function will not continuous function.
yeah,
Yeah,
that is not a
sure.
continuous function,
Yeah,
exactly.
thank
Yeah. So most of the non-rectifiable curves we construct in this manner only. Take a sequence of curves which is converging to a curve, and that convergence curve is not the length is not finite. Basically, all these curves length tending to infinity. In that sense, we construct non-rectifiable curves. Just to give an example, let me mention so that the idea will be clear. Uh, like these kind of functions we have seen. Uh, 0 if t is equals to 0 and t sine 1 by t. Okay, otherwise, so these kind of curves are not rectifiable, like because basically these are not these this function is not a bounded variation. So gamma is from, let's say, 0 comma 1 to r. Okay, so this function is not a bounded variation. So gamma is not a rectifiable curve in R. And also one can use this gamma to construct a curve which is not rectifiable in R2. Observe that this is a uniform limit of these kind of curves. 0 t, where t is basically 0 to 1 upon n pi, and okay. So
And
I hope this is
if
clear. Yes.
so if I restrict the function to the spaces of all rectifiable curve, then the
Mm-hmm.
length function will not be then it is continuous or not.
Uh,
Uh,
okay, so you are asking. Just let me write it.
in
So you
of
are asking
restrict
basically, yeah. So so you are saying that f is a function from space of all curves. Let us say this is the
not
space
space
of
of all curve, rectifiable curves.
rectifiable curves.
Space of all curves, then it is not continuous by your that argument. It's not
Yeah, yeah.
clear.
Uh-huh.
Now this function is not in our it's a real valued function, proper real valued function.
Mm-hmm.
If is goes to R, the f of gamma is the length of gamma.
Yeah, f of gamma is basically length of gamma.
Length of gamma. Then if gamma n converges to gamma
Yeah, then
uniformly,
uh-huh.
then L of gamma, then it should converge. Then it's continuous. I think.
Yeah, because this gamma is already rectifiable, because
Yes.
since we are saying that gamma n converges to gamma, and this gamma is
Mm.
already in this one rectifiable curves.
Mm-hmm.
Yeah.
Fine.
Okay. So okay. So now what we are going to see. Yeah. So this is just a small proof I would like to mention. So suppose LD of gamma is 0, and basically I should write T1 and T2 belongs to A comma B. Okay, and take a partition P which is A T1, T2, and B. Okay, then D of gamma T1 comma gamma T2 is this, basically 0 implies gamma of T1 is equals to gamma of T2 for every T2 A comma B. Okay, and conversely, suppose gamma is a constant curve. So I hope this is clear. This point is clear, I guess. Why distance is 0, because this is always less than equals to length of the curve between these 2 points. Suppose gamma is constant curve, then for any partition we have 0 to n minus 1 distance between gamma tk to gamma tk plus 1, which is 0, and this implies that supremum of this will also be 0. That is length of the curve is 0. Okay, so this is what we have proved now. So if the length of the curve is zero, length of the curve is zero if and only gamma is a constant curve. Okay, fine. Okay, so let gamma be a curve in X, and we let partition P be a partition of A comma B. We denote the module of P by taking the mod of P, just a notation, which is the supremum over all this. I is going from 0 to n minus 1, and D of Ti plus 1 minus Ti. Okay. Okay, so these are just a notation. So Vp gamma and variation of gamma. Okay, so Vp gamma is basically the total variation of gamma with respect to this partition P, and variation of gamma is basically the total variation of gamma. So basically Vp gamma is nothing but this quantity. Okay? And hence the length will be the supremum over all this Vp gamma. So now it is clear that gamma from A comma B to R. Yes.
I just want to know that your in the definition of your modulus of P,
Mm-hmm.
the D of Ti plus 1 or D of
Oh,
gamma
sorry,
Ti
sorry,
plus.
sorry. Yeah, yeah, it will be okay. Yeah,
Yeah, otherwise it's not well defined.
yeah, yeah.
That is
Oh,
clear.
wait a minute.
Uh,
Oh no, sorry, sorry. I have to write something else. Yeah.
no, no,
Okay, this is fine, but here
it's
we
fine.
have
It's
to
fine.
write the here we have to write the
Gamma
modulus.
modulus.
Here we have to write the modulus of Ti plus 1 minus Ti. Okay. So is it fine?
Yeah.
Yeah. Okay. So, okay, so this is a result rectifiability of curves in Rn. So this is basically related to how like uh, gamma is rectifiable if and only if each gamma j is a function of bounded variation. Okay, so this is easy to see. If we have two partitions, P1 which is contained in P2, then the variation of gamma with respect to this P1 will be less than or equals to variation of gamma with respect to this partition P2. Okay, so we will not talk about the change of parameter. Okay, anyways, let me just give an example of curves in non-vector spaces. So this will be, I guess. Okay, so let me just write a definition. So let uh, E be a non-vector space, and we define a so we define a curve 0 comma 1 to E by, so this will be known as the affine curve. Gamma of t is basically equals to 1 minus t into x plus t into y. Okay, this is known as this we will call as affine curve joining x and y. Okay. Okay. So basically it is a non-vector space. So basically we are considering the metric as d of x comma y as norm of x minus y. So here is the result. is length of this under this metric D of this curve gamma is nothing but norm of x minus y. This would be easy to establish, so I will leave it as an exercise. Okay. Okay, so we'll not talk about change of parameters. So let gamma from a comma b to x, and we have another curve sigma with interval c comma d to x, be two curves in x. We say that the sigma is obtained from gamma by a continuous change of parameter if there exists a map phi from c comma d to a comma b, which is continuous, increasing and on to, such that sigma can be written as gamma composition phi. Okay. The map phi is called the change of parameter, and this sigma is called the parametrization of gamma. Is the definition is clear? Okay. So basically the length is invariant under the change of parameter. So we have a curve and we parameterize it and get another curve sigma, then the length will be the same. That is the this is quite an important property. Okay, and for every curve we have this length of gamma is basically the limit of this module of this partition tends to 0, limit of variation of this curve gamma over. Note that we are not taking rectifiable curve, so this can go to infinity also. Okay, and one application of this one is that if we have a curve, then for all c, let us take a curve gamma, and we have a curve gamma, and we take any point c. Let us say this is gamma of c. So the total length of this curve gamma will be nothing but the length of this one, this part, and plus length of this part. So we have the additive property of the length. Okay. So this is quite an important. Arc length as a parameter. So we have a way of parameterizing a curve, which is quite important. For a rectifiable curve, we define arc length function. So now we have a curve gamma from a comma b to x, which is rectifiable. It means that LD of gamma is finite, and we define a function s such that a comma b to this 0 to length of the curve gamma, this interval. Okay, and we define it by s of t is equals to length of the curve gamma restricted to a comma t. Okay, so we have a curve here gamma, and what we are doing is we are just taking so at a particular time t, let us say we are here at the curve gamma, so we are taking this length, we are defining this function, so we are taking this part, length of this part. So s of t is basically the length of the curve gamma restricted to this interval a comma t. So there are some properties of s. So this is known as the arc length function. So s is of bounded variation. This is easy to establish. Just try to do this one. If s is Lipschitz, then so is gamma, right? So for the second property, we have that. Notice that if we have any point t1 and t2, okay, then what we have is t of distance between gamma of t1 is and gamma of t2 is basically less than equals to length of the curve gamma restricted to this interval t1 comma t2. Okay, and which is nothing but s of t2 is s of t1. So it means that if s is Lipschitz, then this curve gamma is Lipschitz. Okay, is it clear? And the other property is S is continuous, increasing, and onto. So increasing property comes from this additive property only, the additivity of length. Continue requires some work. To prove the continuity of S, it requires some work, but it is an elementary way to prove. It is continuous. Basically, the arc length function is continuous. Okay, fine. So this is the theorem, arc length parametrization. So for any rectifiable curve gamma, uh, there is a unique function gamma S such that gamma is equals to basically gamma S composition with S. Okay? And this gamma S is known as the arc length parametrization of gamma, and S is called the arc length parameter. So this is true for any rectifiable curve. It means that any rectifiable curve can be parametrized uh, by its arc length. And this map gamma S is unique. And the important property of this arc length parametrization curve gamma S is that it is one Lipschitz. Okay, so can see the, okay, we will see the proof of this one later. Before that, so any question up to here? Okay, so I hope it is clear now. Okay, so we'll not talk about the length formula in Euclidean spaces. So let gamma be a C1 curve. This length formula is well known, that the basically the length of the curve can be computed via the integration over this thing, modulus of norm of gamma dot t. Okay, so here's one question: what is the most general case for the length formula to hold? Okay. Because see, it would be quite difficult to calculate the length of a curve in general metric space just by the metric definition. Okay, so we want something like this to hold in metric spaces. So we'll see this one now. So the question is, what is the most general case for the arc length? So for the length formula to hold. Okay. So first thing, we need that gamma to be almost everywhere differentiable. Okay. So I will come to this point, what we mean by a curve in general metric space to be differentiable and integrable in some sense. But this problem is, this question is related to the fundamental theorem of calculus. So we recall the FTC. If a function f is Riemann integrable and g is antiderivative of f, okay, then what we have is integral over a to b of fx dx is basically gb minus ga. This is well known to everyone. So this is the fundamental theorem of calculus. And what does it gives? It gives that if f is differentiable on AB and f dash is Riemann integrable on AB, then the integral over the integral from a to b of f dash x with respect to dx is basically fb minus fa. Okay. So at this point, it is important to note some following points. Okay. So note that every continuous function f has an antiderivative. Okay. So in the previous one, we have seen that if the function f is Riemann integrable and g is any antiderivative of f, it is not always possible that every Riemann integral function has an antiderivative. But every continuous function has an antiderivative, and there is a way to construct an antiderivative, which is just by take the integration of integration from a to x f of t and define f of x. In this case, we will get this is the okay. So in general, if f is Riemann integrable, then this whatever f we are getting, it is of bounded variation. But not every Riemann integrable function has an antiderivative. So basically, you make a jump discontinuity. So you take a function f, and so that it is continuous almost everywhere. and you make a jump discontinuity there where it is discontinuous. So once you have a jump discontinuity, it will not be a derivative of some any other function. And the other thing is that derivative of a differentiable function need not be Riemann integrable. That is basically Volterra function. So how do we generalize this thing? Okay, so in what sense we are seeing? Yes.
Hello.
Uh-huh.
What is the role of this jump discontinuity to have this to does not have Riemann I mean antiderivative?
Okay, so like I'm saying that if a function is differentiable, whether its derivative can have jump discontinuity.
Yeah. I mean if dash you are talking about if dash capital if dash.
Yeah, so if f is, so suppose f is differentiable, and can we say that f dash has jump discontinuity because f dash always satisfies IVP?
Yeah, yeah,
I'm,
yeah. So,
Darboux
Darboux
theorem.
theorem. Huh.
hello.
Darboux theorem. Yeah.
Yeah. So if we just define a function like this, 0, where x is not 0, and let us say at 0 it is 1, this function cannot be a derivative of any other function, isn't it?
Yeah.
Although it is a Riemann integrable function.
Mm-hmm.
Yeah. So in this way, we are doing it. Is it clear
Okay.
now? I hope it is clear.
Yeah. Yeah.
Okay. And the okay. So we were discussing about how to generalize this thing. Okay, what is the generalization of this one? Okay, so for that one we need f is almost everywhere differentiable. Also we need to make sense what do we mean by almost everywhere, in what sense. So we will take it as a Lebesgue sense. Okay, so f is almost everywhere differentiable, and again let us say f is Riemann integrable. Okay, okay, so let us do like this. Let us do it like this one. So let us make two parts. So f is, let us say, almost everywhere differentiable, and f dash is Riemann integrable. Other way around, f is almost everywhere and f is basically Lebesgue integrable. Okay? So can we derive to this formula? Okay, f dash x dx is equals to fb minus fa. Can we say in both these cases? Okay? Okay, so if a function has an okay, so this is fine. So this I wanted to mention. So this is a good question to think of. Does every function which satisfies IVP has an antiderivative? Fine. So this is the FTC question. What is the largest class of function for which FTC holds in the Lebesgue sense? Let us recall the Cantor-Vitali function. So this was constructed by Vitali. So this is a function which is continuous, increasing, and at the end points it is u of 0 equals to 0 and u of 1 equals to 1, and it is differentiable almost everywhere, and u dash x is basically 0 almost everywhere. It is constant almost everywhere, but this doesn't hold. Okay, so observe that here u dash is basically Riemann integrable and also Lebesgue integrable, but still, and it is and u is also almost u is differentiable almost everywhere. So basically we are taking all the things what we need, but still the uh, this thing this thing does not hold there. Okay, so what we are missing here? Okay, so again, so this as I said earlier that the length formula is related to FTC. So if you take a Cantor-Vitali function, take a graph of Cantor-Vitali function, that length formula is going to fail. Yeah, this is a good exercise to think of. I think the length will come as under root 2 and something, but u1 and u0 will not be that one. Okay, so the answer to the FTC question were given by Vitali. Uh, so Vitali introduced absolutely continuous functions. So we'll not go into absolutely continuous function because we will remain in the Lipschitz class only. I will not properly mention what is absolutely continuous function because we only need Lipschitz and we will be done with that one. I will mention these things later. So Vitali introduced absolutely continuous functions and proved that AC is the largest class for which FTC holds. Okay. This is just basically a containment of these class of functions. So okay, so basically the Cantor-Vitali function is a bounded variation function, that is fine, but it is not absolutely continuous. So that is what we are missing here, okay, which is absolute continuity. So let me mention the theorem of Vitali. It says that a function is absolutely continuous if and only if it is differentiable almost everywhere. Its derivative is in L1, and for each t we have this one. So basically this integral of the derivative is basically fb minus f. Okay. So this solves the FTC problem. Basically, the largest class is the absolutely continuous function. Okay, so to tackle the length formula, Tonelli introduced the class of absolutely continuous curves and prove the following result. Basically, for any rectifiable curve gamma AB to Rn, uh, any rectifiable curve is almost everywhere differentiable, and this inequality holds. Basically, the Euclidean length of the curve gamma. So this Euclidean length we are calculating in the sense, basically, in the metric sense, the way we have calculated. This is always greater than or equals to integral from a to b, norm of gamma prime t dt. Okay? And the equality holds if and only if gamma is absolutely continuous curves. Okay, so in particular, every Lipschitz curve satisfies this length formula. Okay? As we have seen that any rectifiable curve can be parametrized by a curve gamma s, which is the arc length parametrization, and that gamma s is basically one Lipschitz. Okay? So we can take any rectifiable curve and we can work with his arc length parametrization. That arc length parametrization is Lipschitz. Okay, so this is the length formula by an arc length. Okay. So here we have the theorem. So for any rectifiable curves, as I mentioned earlier, this is basically gamma dot t. We can write it as basically s dot t, and with equality only for the if and only if gamma is absolutely continuous. Okay, so this is in Rn. Like for our question of length formula, we have find a condition in Rn. We're now going to see the analog of the length formula in the metric space setting. So for that, we need some notion through which we can say that a curve is metrically differentiable. So this is a notion of metric derivative. So we say that a curve gamma is metrically differentiable at t if this exists, if this limit exists. Okay. Recall that the way we define the differentiability of a curve gamma. So uh, this is an exercise, like it's an easy exercise to prove that vector converging to vector, then norm will converge to norm. Okay, so we are just taking that norm part, okay, and we are replacing the norm part with the distance function. So this in the norm sense, this will be basically gamma of t plus h minus gamma of t limit s tends to 0. Okay, so replacing this norm part by the distance. Okay, so we say that if a curve, okay, so this is a theorem. If a curve is Lipschitz, then its metric derivative exists almost everywhere, and this is integrable. So this is the result, and this is integrable from a to b, and the integration of this quantity is nothing but the length of the curve gamma. So this is quite an interesting result, that for Lipschitz curve we have the length formula. Any doubt up to here? Okay, we'll move ahead. Okay, so this is regarding the length formula in metric spaces, and Now we'll see about how to, like, what does it mean. Uh, so just wait a minute. Yeah. So let rho be a Borel function and gamma is a rectifiable curve. So we want to make sense of this quantity. What does it mean? How to define it? Okay. So what we're going to do is parameterize gamma with respect to the arc length. We will get gamma s. Okay. So basically, gamma is composition this arc length function. Okay. And then in this case, because of the Borel property, rho composition gamma s is going to be Lebesgue measurable. Okay, so this is Lebesgue integrable because this has finite measure, and hence we can do this one. So this quantity is well defined. Is it clear? And we are going to take this quantity as as our as our definition. So I hope it is clear. Okay, so the definition of basically rho over the curve gamma. So the integral of rho over the curve gamma is nothing but this one. Furthermore, what we can do is basically we can write it as if you just want to make this derivative from a to b, something like rho of gamma s t, and this will be gamma s prime t, and this will be dt. Okay. Any doubt? Okay, so we'll now see the uh, proof of the arc length parametrization. Okay. So we'll divide this proof, this theorem proof into two lemmas. Okay, so the first lemma is basically uh, let gamma such that a comma b to x be a rectifiable curve. Then for each u belonging to 0 to this LD of gamma, there there exists a unique point x belongs to gamma and a point t belonging to a comma b such that basically x is nothing but gamma of t, with length of this curve gamma from a to t is nothing but u. Okay, and further this is the important point. Furthermore, the set of such points t associated associated to U is a closed subinterval of AB, okay, and the map gamma, and the map gamma is constant on this subinterval. So this will say as this is one such lemma. So we'll see the proof of this one. Okay, sorry. So proof is basically simple. So basically what we're doing is this map S, which so S from A comma B to 0 of LD comma gamma. This so S of uh, so basically this T going to length of this gamma restricted to basically A to T. This is basically continuous. This function is basically continuous. So uh, so we can use the intermediate value property IVP. Let us say intermediate value theorem that every continuous function satisfies IVP to obtain for every u satisfying 0 is less than or equals to u between LD of gamma, a real number T satisfying L length of this gamma restricted A to T is basically U. So I hope this is clear. Okay. Now, if T and T dash are two real numbers, are two real numbers satisfying T dash to B, and length of gamma restricted to A to T is basically the length of gamma restricted to basically A to T dash. Okay. Then by the additivity property, we have basically length of this curve gamma from T to T dash is basically 0. Okay. And this implies that gamma is constant on the interval on the interval t to t dash. Okay. So basically, it means that the set of points which is set of real numbers t associated to u, basically they form a subinterval of a comma b. And okay, so basically this gives, okay, wait a minute. So basically this gives us that so we have a point u in this interval u from 0 to the length of the curve. Using the IBP, we got a real number t such that length of the curve from a to t is basically u. Okay, now the collection of all these t, okay, forms a subinterval of a comma b. Okay, on which the curve gamma is constant. And moreover, since this map t going to, okay, so moreover, since this map LD of gamma a to t, this is continuous, this subinterval is going to be closed. Interval is closed. Okay, because they are in inverse image of a singleton point, so that is going to be closed. Okay, so I hope the idea is clear what is going on. So what we have done, so basically what we are going to do is that what we need gamma s. Okay, we need, wait a minute. So we need gamma s, so that gamma is basically equals to gamma s composition this with this arc length function. So if we take a point u in this one, 0 to LD of gamma, okay, we need a point in x and also in a comma b, so that at that point uh, s of t will be basically u. Okay, and gamma s of this will be a unique point which will give the x in the metric space L. This is basically the curve gamma. So this is the whole point. Okay, so for that one we need the other lemma, which is lemma 2. So let gamma such that a comma b to x be rectifiable curve. Okay, and consider the map gamma s from, let us say gamma s only, let us say 0 to LD of gamma to this metric space X. This is defined by gamma s of this point. Let's say a point u, and then use the proposition. We'll get a point t, and we'll define gamma over t. Okay. Okay. So where, remember, as I said here, that this gamma of, yeah, in this lemma, so this is a unique point X. Okay, so basically where this gamma of t is unique. is unique. Okay. Unique point of X. And this satisfies length of T, basically U. Okay. So in this case, the map gamma S, the map gamma S will be one ellipse. Okay. So this is fairly easy to prove. So this is the way we define the arc length parametrization of the curve gamma. So this everything is fine. Yeah. Whether the proof is clear, basically how we are getting the arc length parameterization of a curve gamma.